Okay, what we are doing today is we are going to learn a new number system, a new set of numbers. This is exciting. So everything that we have done up until this point has been with respect to real numbers, factoring with respect to real numbers, graphing with respect to real numbers. Well, what we are being introduced to today is something known as a complex number. So if we think back to everything that we've done so far, remember when we built the number line, if you recall, we had our real number line. And if we remember, we represented that with the symbol as the double struck bar R, right? So that was our set of real numbers. We looked at the real number line and then we said, hey, I have some natural numbers. Remember, we are counting numbers 1, 2, 3, etc. Then we added 0 to it. Remember? And we had our whole numbers. So then we had our whole numbers. And then from our whole numbers, we added negative numbers. And then we had, so we took these counting numbers, these natural numbers and 0, and we took their opposites. So we introduced those negative numbers, and that gave us the integers. Then we looked at all those little numbers that could potentially be inside, in between, as well as our integer values, which could also be represented as fractions, but also these fractional parts of whole numbers, and that gave us the set of rational numbers. And then in addition to those rational numbers, numbers that we could represent as a ratio, right, of whole numbers or integer values, we looked at those rational numbers, and then we looked at repeating decimals. And we said, hey, what if we have a number that goes on forever and ever and ever, doesn't repeat without a path? Numbers we can't represent as fractions. We introduced those irrational numbers. The combination of the rational and irrational numbers led us to the set of real numbers. That's what we've worked with so far. Now, if I take numbers that don't fall on the real number line, and I introduce something known as imaginary numbers, the combination of imaginary numbers with real numbers gives me the set of complex numbers. So complex numbers have a real and imaginary part. So let's go a little bit more in depth into the real numbers and compare and contrast those to what we are talking about. So if I have my set of real numbers, the way we represented our set of real numbers, well, it was a union of rational numbers and irrational numbers. Okay, that's what built rational numbers and irrational numbers. If I took the union, meaning include everything in those two sets, I got my real numbers. In contrast to my real numbers, I have imaginary numbers. Now, imaginary numbers are not real. The way you want to represent imaginary numbers using set builder notation, well, it's going to be the set of all values x such that x equals ai, where a is just a real number, an element of the reals. A cannot equal 0, or else I have x equals 0, because anything times 0 is 0. But most importantly, I is equal to the square root of -1. I equals the square root of -1. So now we can address radical expressions that have a negative radicand. And we call this the unit imaginary number. So if I give you I you need to know that equals the square root of -1. So how do I represent the set of imaginary numbers? The set of imaginary numbers is I, capital I, and it can be double struck. So some examples of imaginary numbers. Well, I literally can give you the square root of -1, and I've given you the unit imaginary number. I could give you the square root of -25. Now, before, if you had just the square root of 25, that would be 5, right? 5 times 5 is 25. But once I have a negative in the radicand, you have an imaginary number. So the square root of -25, well, I can look at it as 25 times -1. Square root of 25 times the square root of -1, 5i. So we don't leave negatives in the radical, just like we don't leave radical expressions in the denominator, or negative exponents. We don't leave negatives in the radical. We introduce I.
Instead of do we have to do we try to get I out of the equation, or we'll have to solve the equation using?
You can have I. You can't have I in the denominator. Good question. And we'll do a few of those. So what if I give you the square root of -75? You would still look at that as the square root of 75 times the square root of -1. Can you simplify the square root of 75? What would it be? 5 times what? No. 5 times the square root of, no. 75 is 25 times 3, right? Isn't it?
Oh, I.
Square root of 25 is 5, square root of 3, and then this square root of -1 is I. So the coefficient of I here is 5 times the square root of 3. So while you're working with imaginary numbers, they do have a real coefficient. How many i's am I giving you? How many unit imaginary values am I giving you? I'm going to perform operations on imaginary numbers. Now, that's what an imaginary number is. What if I say, well, what about complex numbers? What's a complex number? What's the difference between a complex number and an imaginary number or a real number? Well, if you look at this up here, the combination of real and imaginary numbers yield the complex numbers. So a complex number has a real and an imaginary part. To represent it in set builder notation, it is the number x, such that x is represented as a plus bi, where a and b are just elements of the reals, and I is the square root of -1. So if you notice, a plus bi, which is a complex number, well, if I represent it in that form, a plus bi, that is what is known as standard form. Standard form has a real part, or complex numbers have a real part, and they have an imaginary part. We always represent complex numbers in standard form. Do not give me the imaginary part first. That is not best practice. Best practice is that we represent all complex numbers in standard form, meaning the real part first, plus or minus the imaginary part. How do I represent the set of complex numbers? The set of complex numbers is a double struck C. Complex numbers. Makes sense. So let's look at some examples. One thing I want you to keep in mind is that any number can be represented as a complex number. You can always represent it as a complex number. However, the real or imaginary part could be 0. So let's look at some examples. Examples of complex numbers. If I give you 1, that's real. But can I represent it as a complex number with a real and imaginary part? Sure. What would it be? 1 plus 0, I. Beautiful. What if I give you 1/2? What type of number is that? Real. What else? Rational. Okay, good. And can I represent it as a complex number? Sure. 1/2 plus 0, I. What if I give you pi? What type of number is that? Real. What else? Irrational. Can I represent it as a complex number? Pi plus 0, I. Very good. What if I give you 5i? What type of number is that? It's imaginary because it has I in it. But can I represent it as a complex number? What would it be? Very good. And we'd have to write it in standard form. What if I give you negative 3i? 0 minus 3i as a complex number. Very good. What if I give you 2 times the square root of 3i? Can I write that as a complex number? Beautiful. And again, we want to make sure we always represent complex numbers in standard form, and you will see why. Yes.
When you have I with the coefficient in an equation, can you treat that coefficient like a regular number and divide it off the other?
Yes, absolutely, because these are connected by multiplication. Absolutely. Yes. Yes. Can you?
Dr. P.
Yes.
Is the I like inside of the radical or is
No.
it outside?
It's outside because inside the radical, it would be represented as a -1.
Okay.
Right? And I took it out. So I could rewrite it if I really wanted to. I mean, I'm not, but I can do this, right? And I can even go so far as to say this, right? I mean, but we won't, right? But you could, right? Okay, so of course I'm not just going to give you an I. I'm going to give you different powers of I, but there is a pattern that I want you to be able to recognize, because if you're working problems that have powers of I in them, we should be able to simplify them. So if we keep in mind that the square root of -1 is our unit imaginary number I, bless you, meaning I have one I, what do you think I to the 0 would be? 1. I to the first is just I. I squared is the square root of -1 times the square root of -1. What do you think that's going to give you? -1. What about I cubed? Isn't that just I squared times I? I squared is -1 times I would give me what? -1i or -I. So just take a moment. I to the 0 is 1. I to the first is I squared is -1. I cubed is -I. All right. What about I to the 4th? Isn't I to the 4th just I squared times I squared? So it's just 1. I to the 5th? Positive I, right? Because it's just I to the 4th times I. I to the 6th? I to the 7th? Do you see the pattern? I to the 8th is what? Then next power of I, and I to the 11th. So if you can remember this, and you know that it occurs every 4 terms, every 4 powers of I, if you know that pattern, it's very easy to evaluate powers of I. So you better believe on a quiz or a test, I'm going to give you I to a number. Okay? I could give you any number I want. I could give you I to the 1001 power. Oh heavens, how could we do that? If we know that it happens for numbers divisible by 4, it equals 1. If you divide that exponent by 4 and you get a remainder of 1, that's like I to the first. If you divide the exponent by 4 and you get a remainder of 2, it's like I squared, -1. If you divide the exponent by 4 and get a remainder of 3, it's like I cubed, it's -I, and so on, right? You're never going to have a remainder greater than 3 because then it would be divisible by 4 for the next one, and so on and so on. Does that make sense? So if I gave you I to the 1001 power, well, what would you do? You would take that exponent and divide it by 4. Okay, 4 into 10 is what?
250.
Okay, well, it is 250, but in case we forgot how to, because that's coming up next, right? Make sense? But then I'd have a remainder of 1. I'd have a remainder of 1. So this simplifies to I to what power? The first power, which is just I. So given I to a power on a quiz or a test, you're going to divide that exponent by 4 and see what the remainder is. The remainder is going to clue you in to which of these 4 you're going to use. Make sense? Okay. Now, let's say you have complex numbers and you want to perform addition or subtraction of those complex numbers. It's just combining like terms. It's not hard at all. So you're going to have real parts that in this case you could add together, or you could have real parts that you're subtracting. And then you do the same thing with the complex parts. So let's look at the first example. I have a complex number plus another complex number. Now, what's very important, the biggest mistake people make is they don't pay attention to this operation. They start doing all these crazy things to these different parts of these numbers. Notice whether it's addition, notice whether it's subtraction, multiplication, division, etc. Because that changes how you're approaching the problem. So in this case, I'm going to look at my real parts. And if I add my real parts together, what do I get? Okay. And then I'm going to look at my imaginary parts. Oops. And I'm going to add my imaginary parts together, and what am I going to get? Plus 5i. And again, we want to write our answers in standard form. So I need a connecting operation here. Is it a positive 5i? Is it a minus 5i? You must write your answers in standard form. You will lose points. I'm telling you right now, you will lose points if you do not write your answer in standard form. Okay, let's look at the next one. Add the real parts, add the imaginary parts. Oh no, subtract. Subtract the real parts. So I have -7 minus -9, which gives me what? Okay. And then I have positive 5i minus a negative 11i gives me, so plus 16i. Make sure you write it in standard form. These aren't two separate numbers. That is one complex number with a real and imaginary part. Okay, let's look at the next example. Combine like terms and tell me what you get. Simplify that, and what do you get? I agree 100%. And again, we're writing it in standard form. Okay, so addition and subtraction. Yes, sir.
I don't think I really taught on the powers of I.
Mm-hmm.
So if it's remainder 1, that means it's
I to the first. Mm-hmm. The remainder is the power of I.
Okay. And then, but if there's no remainder, that means it's the.
Then it's just 1, right? Because I, right. Mm-hmm.
Okay, that's.
Makes sense? Okay. Now, why am I stressing the fact that you want to write your numbers in standard form? Well, if you look at a complex number in standard form, we need to be able to represent the additive inverse of a complex number. So the additive inverse, remember, you're asking yourself, what am I adding to this to get 0? So what am I adding to A to get 0? Negative A. What am I adding to BI to get 0? Minus BI. So the additive inverse of this complex number written in standard form, you take the opposite of each term. The opposite of the real part, opposite of the imaginary part. How do if I can verify this, I can take this and then I can add. And I got 0 plus 0 I. That's hideous.
So even if the situation is not right as 0 plus 0.
Well, I'm just showing you the complex conjugate. I mean, sorry, the additive, I gave away what we're doing next. The additive inverse. So if I give you a number, you're going to write it in standard form, and then you're going to give me the additive inverse, right? That sounds like a great multiple choice question. I give you a number, and you say, which of the following is the additive inverse? You may think that's easy, but not as easy as it might be. Now, here's a little just brief history. There is a sheet that I put together that's on the portal that has, I may have copied it in there, I can't remember, but it's on the portal, just a little bit more history. Is it in there? I see it. Okay. So in case you want to know how to graph on the argon plane, the complex plane, it's not like the Cartesian plane. So just a little bit additional information. Of course, it dates back to the Greeks. Of course. Now, multiplication of complex numbers. I give you a complex number A plus BI. I tell you to multiply it by a complex number C plus DI. These are binomials. You just FOIL. At the end of the day, you address any powers of I if they can be simplified. So again, notice here that I am multiplying. There's no plus here. There's no minus here. This is multiplication. So the operation that you're performing makes a difference on how you're going to address the simplification. So if I want to multiply these, let's FOIL. If I multiply the first terms together, what do I get? Huh? Negative 8. If I multiply my outer terms together, what am I going to get? Plus 2i. Make sure you put connecting operators, please. If I multiply the inner terms together, what do I get? Plus 24i. And if I multiply my last terms together, ooh, what do I get? That, very good. Now, let's combine like terms and simplify where we can. Okay, what can we combine for starters? Okay, what am I going to get for that? Okay. Is there anything else I can simplify? I squared becomes -1, yes. So really, -6 times -1, what does this become? +6. Is there anything else I can combine and then represent this in standard form? Gives me what? Okay, so I have in standard form, it's the simplified form, -2 plus 26i. That's your answer. Okay, let's try the next one. Let's distribute, right? Because this is just distribution. If I distribute, what am I going to get? Is there anything else I can do to that? No, it's in standard form. I'm done. Okay, let's distribute here. What am I going to get?
-6 plus 24.
Okay, so this we said becomes -1. As soon as you see that I squared, boy, you're going to use that like you wouldn't believe. Becomes +6. So that gives me, ooh, that's an I. We forgot an I. There we go. So that's really 6 plus 24i in standard form. Now, Again, you want to represent your complex numbers in standard form because we could take the conjugate of that. Conjugate is not the additive inverse. Remember, additive inverse, we take the opposite of each term. The complex conjugate in this case, we are only taking the opposite of the connecting sign. So these are called complex conjugates. Oops. Complex conjugates. And something very beautiful happens when you're dealing with complex conjugates. If I were to FOIL these, what am I going to get?
Oh, you're gonna get a single number.
Well, I don't know, you tell me.
Yeah, you're gonna get a squared plus -1 times b squared.
What is it going to give me when I combine like terms? Okay, let's do it. A squared minus ABI plus ABI, right? Minus B squared I squared. You see how I FOIL?
Oh, it's just
Yes? Okay, so then these are opposites, leaving me with what?
a squared plus.
Well, this becomes -1.
A squared plus B.
A squared plus B squared. Look at that, the sum of two squares. So when we were factoring over the reals, we couldn't factor that. We could only factor the difference of two squares, right? The difference of two squares is factorable over the reals. A plus B, A times A minus B. A squared plus B squared, we cannot factor over the reals, but I can factor over complex conjugates. So yes, you can factor this.
So you can factor the difference of squares and the addition of squares.
Using complex conjugates. Yes, 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 yes. Isn't that beautiful? It is beautiful. All right, let's do some more operations. You are now being asked to divide with respect to using complex numbers. We do not ever leave I in the denominator, just like we didn't like to leave radical expressions in the denominator. We rationalize the denominator. What does it mean to rationalize the denominator when we're dealing with imaginary numbers? Well, we have to multiply by perhaps conjugates so that we can get rid of that I. So looking at the first one, there's not really anything to do to the first one, right? The only way to simplify is to give that denominator to each of the terms in the numerator, because that's a binomial, and then simplify that, which would be 7/2 plus 2i. So this would be the simplified form in standard form. Now, looking at the next example, what on earth do you think you are going to multiply this fraction by? Making it an equivalent fraction. We're not changing the value of the fraction. We're just addressing the fact that it has an I in the denominator. What's the easiest thing that I can do?
Multiply by 1.
No. Well, couldn't I just multiply the numerator and denominator by I? I really just want to get rid of an I. Could you multiply by something larger like 5i or -5i? Absolutely. But then you're going to have to simplify the fraction as you go along. Okay? So we have to be clever about what we choose. There's not just one way to do it, but there's an easiest way to do it. Now, I am multiplying the numerator, that binomial, that complex number by I. So that means I am distributing by multiplication over addition, right? So what is that going to give me in the numerator? Okay, and in the denominator, what do I have? Okay, now, as soon as you see those I squareds, you know they each equal what? Okay, so clean it up. So that's going to give me 7i, and then what's left in the numerator? Okay, and in the denominator, bless you, what do I have? Do I stop there? That's not in standard form. Standard form says I have to have a real part and I have to have an imaginary part. There's the imaginary part. There's the real part. Is that in standard form? No. No, I have to do more. A little bit more. I have to rewrite it. Commutative property of addition says that order can be interchanged, right? There's my final answer. Simplified and in standard form. Now, notice that you have a complex number in the denominator. What do you think you have to multiply the numerator and denominator by to rationalize the denominator here? The complex conjugate, which is? It's not, you couldn't just multiply by an I, because then when you distributed it to the first term in the denominator, you get an imaginary number. So that is why we are addressing it by rationalizing the denominator, in this case, multiplying by the numerator and denominator by the complex conjugate. So if I FOIL in the numerator, FOIL the numerator, what am I going to get when I FOIL the numerator? Tell me. I can write as much or as little as you tell me. Ooh, y'all are trying to do it all the way, huh?
Oh, wait, for the denominator?
Numerator.
Oh,
Numerator is -6 plus 43.
I agree with you.
The denominator should be 20.
You are correct. Is that my final answer?
No, it's not.
What is my final answer?
-6/29 plus 43/29 I.
Yes. Simplified and written in standard form. Hopefully you can perform the multiplication and simplify. Combine like terms, address I-squareds. Now, as I mentioned to you, as soon as you get a negative inside the radical, if your radicand is a negative number, you have now introduced imaginary numbers into the problem. You can't just use those properties when we were dealing with it from way back when. You cannot combine these inside and just turn this into 36. That is not correct. I don't even like to write it. Okay? As soon as you introduce a negative in the radicand, you are imaginary. You cannot come back from that until you simplify everything in the problem and perhaps it goes away. So how would I address this? Well, I'd look at this as square root of 3 times square root of -1, square root of -1, square root of 12. Do you see how I just separate? I just like to separate my negative ones because then I know their I's. Okay, so what is that going to give me? Well, that's going to give me the square root of 3I times another I. Can I simplify the square root of 12? What would that be? 2 times the square root of 3, right? Now, I can combine my I's. What is that going to become? That is going to become -1. Can I combine these? If I multiply those together, what do I get? So what is my final answer? No I. You can put +0 I don't care.
Dr. P, what if you could you turn each one into 3I and 12I and then multiply them together to get 36I?
Square root of 3I.
Yeah, square root of 3I and square root of 12I.
That's kind of what we did, except we did 2 steps in one because we simplified the square root of 12. Absolutely.
I find it interesting. I just tried to plug that in on my calculator, but it wasn't able to do it.
Because you're under the reals. You have to change it to working with complex conjugates. I mean, complex numbers. So I'll show you how to do that, but you really don't want to be messing with that.
I just wanted to do what would happen.
Yeah, it's not going to work because right now you're in the mode of real numbers. You can change it to complex numbers, just like if, well, y'all haven't done pre-cal. Yeah, there's lots of things you can change. Degrees to radians, a lot of things. Absolutely.
Right?
Oh, super exciting.
Is there a way to express um, uh, an imaginary number in some kind of visual sense, like a graph or a number line?
Yes. Yes. I'm going to say yes. I'm not going to spend time right now until we finish the notes. I did put a link onto where you can see more about how to graph them. You will see them also when you deal with vectors and in physics. And if you do any circuitry and computer science there too. Yeah, there's lots of applications. Okay, what about the next one? What if I give you the next problem and I ask you to simplify that? You think you can do it? Of course you can. Go ahead, tell me what you get. Beautiful, that is absolutely fantastic. Does everybody see how?
Yes.
Anybody not? We need to show the steps. We're good? Okay, now one thing I want to remind you again is that there's a difference between solving and evaluating. Solving means you have an equation and you're looking for the value of a variable. So at the end of the problem, you have x equaling some type of number, let's say. If you are just being given an expression, there's no relation in there as far as an equality or an inequality, then you're just simplifying. Okay? So you really need to make sure that you use these terms correctly, right, when we're talking math. We're honor students, we need to speak mathematically correctly. Okay? That's all I have for you as far as the formal notes are concerned. You do have a my math lab on this, so make sure you do your my math lab. And then I want to point out one other thing that I would like you to do before we come back to class on Thursday. So in the notes, if we're looking in the notes, the next thing we're going to do, and the reason we introduce these imaginary numbers is because now we're going to start working with quadratic equations, meaning when you square root both sides, you may get the square root of a negative number. So now we can address that in terms of I. So what I would like you to do, because this is what we're going to do on Thursday, is I would like you for Thursday, if I can find, is it not here? I'd like you to do this. And it should be fairly quick because you can use Desmos in your calculator. Okay? So please do this exploration. It's similar to what we did for transformations of absolute value functions. So we're just looking at a specific form known as the vertex form. So you've been given this equation, and we're just exploring different values of A, H, and K. Okay? So again, just like we had the parent absolute value function and we looked at transformations, how A affected things, how K, we looked at this before. This is an analogous exploration where we look at the parent function and then we change these different values of A, H, and K. So here are some tables that I would like you to populate. If you want to use your calculator, you can to help you with the arithmetic, because we're going to explore, compare and contrast what's happening and how changing A, H, and K. So then here we change K. And looking at the graph, and again, I would do all these in Desmos. And then here we're going to look at changes in in K. Okay? Sorry, this is H. So we're going to explore changes in H, changes in K, changes in A. How does that affect the graph of your quadratic function? Then after you investigate those tables, I want you to draw a conclusion. And again, if you know your transformations from the absolute value function, this should be ringing big bells. This is exactly the same transformations. Okay? So go ahead and do this exploration and the 1.4, my math lab for Thursday. We will start Thursday by going over this.
This is all due Thursday?
Yes, yes. So again, this should not be fast. In fact, if you want to do this part in class today, you can, and then just save the my math lab, if y'all want to do that. Yes,
Where is it in the note? Can't find it.
24,
Where
No, 23.
right here.
Actually, we have different numbers.
You have different numbers. Well, there it is. Quadratic equations exploration. So do those 3 pages as just an exploration, and then we'll do 1.5 B notes, B and C actually, in class on Thursday. Okay? All right, so y'all can work for the rest of class. Is there any, I see a hand up online, so let me look at that.